computer. Okay, let me start. Okay. So, saya akan mulai. Assalamualaikum warahmatullahi wabarakatuh. Selamat sore rekan-rekan mahasiswa sekalian. Yang saya hormati Pak Novanto Yudhistira dari Informatika UB, kemudian His Excellency Dr. Noman Naseer from Air University Pakistan. Hello, I hope you have a good time in there. Kemudian yang saya hormati Pak Ardi Imawan dari PT DOT Indonesia. Halo Pak Ardi, apa kabar?
Baik.
Oke, dan rekan-rekan mahasiswa sekalian yang saya banggakan, alhamdulillahirobbilalamin, puji syukur kehadirat Allah Subhanahu Wa Taala. Hari ini kita bisa bertemu di kelas pembelajaran mesin lanjut ya. Mungkin ini surprise buat teman-teman. Saya perlu menyampaikan bahwa teman-teman di sini akan mempunyai pengalaman yang sedikit berbeda dengan mahasiswa yang lain. Teman-teman bergabung pada kelas yang menggunakan konsep 3-in-1. Nah, apa itu 3-in-1? Dalam kelas dengan konsep 3-in-1 ini teman-teman akan diajar oleh 3 orang yang sangat berpengalaman sekali. Satu orang dosen dari Informatika UB, Pak Novanto Yudhistira, kemudian ada 1 orang dari Air University Pakistan, Dr. Noman Naseer, kemudian yang ketiga nanti akan ada juga dari praktisi industri, yaitu Pak Ardi Imawan dari PT DOT, yang kebetulan saat ini lagi ada di Jepang ya. Jadi itu 3 orang yang nantinya akan bersama teman-teman selama 1 semester untuk belajar tentang pembelajaran mesin lanjut, atau kalau dalam bahasa Inggris adalah Advanced Machine Learning. So, selamat datang di perkuliahan pembelajaran mesin lanjut. Mungkin saya akan sedikit memaparkan tentang para lecturer kita sebelum nantinya akan dilanjutkan dengan sesi dari Dr. Noman Naseer. So, I will translate to you what I said before. Okay, so I said welcome to every student to the Advanced Machine Learning class. This is a great opportunity for them to join this class because they will be taught by 3 distinguished lecturers. First is Dr. Novanto Yudhistira from Brawijaya University, and the second is Dr. Noman Naseer from Air University, and the third is Mr. Ardi Imawan from DOT Company Indonesia. And in this course, they will absolutely get a very good experience both in a theoretical approach of the advanced machine learning as well as the practical approach. Okay, that's what they will get in this course hopefully. So I will present something to you before you can just continue the learning with Dr. Noman. So let me Okay, so I will briefly introduce the 3-in-1 program that held by the Brawijaya University. So actually, what is 3-in-1 program? Is a program from Universitas Brawijaya to leverage our education quality by performing joint lecture involving UB Academia, professor from abroad, and 1 expert from industry. So this is the 3 experts involved in this class. At first is, of course, Pak Dr. Novanto Yudhistira. He is a lecturer and researcher of the Brawijaya University Indonesia, and he got a PhD from Hiroshima University, and he is an expert in deep learning. So he's a kind of very have a good and deep understanding of the advanced machine learning. And our second expert will be Dr. Noman Naseer. He is a lecturer and researcher at the Air University, Pakistan, and he got the PhD from Pusan National University with the expert in brain-computer interface, smart system, mechatronics, as well as the smart system. So like machine learning, deep learning is very good at that topics. And the last will be Mr. Ardi Imawan. He is the Chief Technology Officer of PT DOT Indonesia, and he got the Master of Science from Pusan National University. Actually, both of Dr. Noman and Mr. Ardi is my friend in Pusan National University. So thank you very much for helping us to do this kind of 3-in-1 lecturing. So Mr. Ardi is an expert in software development and project management. He got very much project from both the government and from another company. So that's all the expert that will be involved in this 3-in-1 lecture. And this is our academic calendar in Brawijaya University. I believe every student already got this material in the first meeting. So actually this is the second meeting of our class. So the first meeting was conducted in the last week. So this is the second week. And we will finish our lecture around at the end of November. And we will have the final exam around December, and the midterm exam around mid of the October. And what is advanced machine learning? In this course, the student will learn the advanced topic in machine learning, such as deep learning, including convolutional neural network, recurrent neural network, all together with their implementation. And this is a kind of the elective course with 3 credits for student in 5th or 7th semester. And for the prerequisites, I believe you already got the introduction to machine learning, or in Indonesia, pembelajaran mesin lanjut. I believe you already joined that course and graduate from that course. And also, I believe you already graduate from artificial neural network course or jaringan saraf tiruan in Indonesia. So I believe you already got those 2 courses. So you will not have a big problem to join this course. And this is the course participant. We open this course for 2 kind of students. One is the normal student. This is UB students, or optionally from another university, if any. And this should program this course in their transcript plan, and at most 50 students. I asked Dr. Novanto and the student of this class around 40 students. So it will not be a big problem. And you should actively involve in the course, like doing quiz, homework, and in the end we will have a student project. And you are the subject of this grading. And apart of that, we also have the open participant. It can be anyone, including another lecturers, and at most 150 participants. So we are using a licensed Zoom. So maybe we can get maybe more than 150 if any, and optionally can also do the student project, but the grading is optional for the open participant. So for the tools, maybe we will use the E-Link. E-Link is a kind of Moodle-based learning management system built by Faculty of Computer Science, and also we can use the Zoom, and we maybe some library that you will use in this course, maybe for Python using PyTorch or TensorFlow, and we also provide some cloud-based development using AWS, or you can also use the Google Colab or GitLab. Anything that needed in this course, our study program will provide it for you. Okay, so that's all the introduction of this course. I hope everyone in this course will have a very, very pleasant journey during this semester. So that's all my opening. Is there anything you would like to say to student? Pak Yudis, mungkin ada yang mau disampaikan?
Okay, thank you, Mr. Bawyuka. This is our first time for doing 3-in-1 course in advanced machine learning, and hopefully you will enjoy the course by another lecturers like Dr. Noman from Pakistan will deliver based on his experience and his expertise, and also Mr. Ardi from DOT from the practical perspectives. So it will enrich your understandings of this course, not only from a theoretical perspective, but also in practice. So please enjoy and do your best in this course. Thank you very much.
Okay, thank you very much, Dr. Novanto Yudhistira. And the next, maybe from Dr. Noman Naseer, is there anything you would like to say to the students?
Yes, sure. So, I mean, the idea of 3-in-1 is very fascinating, actually. We've been thinking about it since long, but we could not implement it yet. It's interesting to see that UB has succeeded in this mission, and they're doing it, actually. So, I mean, I'm very fascinated by this idea. Along with the theoretical aspect, we should get to know about the practical aspects, how to deploy things, how to implement those things. And also, if you get to know about a topic, about a subject from different experts, you get the different point of views, you get the different dimensions of learning. So it's a very fascinating idea, and I hope that you'll learn a lot and you'll enjoy the course. Thank you.
Okay, thank you very much, Dr. Noman Naseer. And the last, maybe some speech from Pak Ardi Imawan. You can use either Indonesia or English. It's okay.
Okay, thank you. Can I use Japanese?
Oh, of course.
Okay, thank you very much for the opportunity. So I think it's very interesting because lately in 3 years ago, I start to come into several university to talk about industry because there is so many gap between university and the industry itself. So right now there is a 3-in-1 program. I think it's very interesting to acknowledge the student about how the industry works. So maybe I'm not too expert about the deep learning, just like Dr. Noman or Dr. Novanto, but I can share the experience in industry, how we build something that maybe you learn from university for industry needs. That's it, I think. Maybe the last one, hopefully you enjoy the course. This is a very interesting topic, and also the technology is actually the technology is not the technology is not to it's not a new method, but nowadays it used. 1 decade ago, 10 years ago, I learned about this technology, but we never use this technology because there is no need, there is no demand on a market. But now everything talk about AI, everything talk about deep learning and etc. So I hope you enjoy the course and get something from this class. That's it. Okay, thank you.
Okay, thank you very much from Dr. Ardi, and that's all the opening ceremony, essay opening ceremony, because all the lecturers come here in this session. So for the closing of the opening ceremony, let's have some good photo session first, and then after that you can continue the learning with Dr. Noman as in the schedule. Right? Okay, so everybody, please turn on your camera and have a very best of your pose. Okay, we have now 42 participants. Okay, I will take the picture from the first slide. So please smile with your best smile. So say cheese, cheese. Okay, now I will take for the second slide. So please have a good smile. So cheese. Okay, so thank you very much, Dr. Novanto, Pak Ardi Imawan, and Dr. Noman Naseer for coming in this session. So for the next, I will give the time for Dr. Noman to continue for the this class. Right, so thank you very much once again for Dr. Noman, Pak Ardi, dan Pak Novanto for arranging this kind of course. Is very, very helpful for our students. Hopefully we can make this kind of course continually, maybe next year and next semester and so on. So thank you very much. I say Assalamualaikum warahmatullahi wabarakatuh. So please, Dr. Noman, you can continue this session. Okay.
All right, I'll just turn off my video so that my voice is clear and there's no distortion. Okay, let me share the screen. So I hope my screen is clear and the slides are clear too. Please do interrupt me and let me know if you face any problem with the voice or in the slides. Do let me know. All right, so as you know, this course is Advanced Machine Learning. And today's topic is basically based on supervised, unsupervised, self-supervised, and reinforcement learning. Most of my presentation material is provided by Professor Noman. I've just added a few more things and I'll add my insight into it. I'm, of course, as Aditya introduced, I'm Noman Naseer, and I'm a tenured associate professor at Air University in Islamabad. I'll just briefly go through my introduction so that you know who is teaching you, and then we'll go on to the contents. I'm a tenured associate professor at Air University Islamabad. Tenured associate professor is actually a tenured or a permanent position, which is highly prestigious, and I recently got it. In fact, I'm the youngest person in the history of the country to get this tenured associate professor position. Also, I'm the first one in engineering departments in Air University to get this position. I'm also heading a neurorobotics research group where my actual field of expertise or area of expertise is controlling robots through neuronal signals or brain signals. Of course, when we do that, we have to take help from machine learning because we get signals from the brain, and those signals we need to discriminate through different machine learning algorithms. For decoding and discrimination, we use classifiers or ML algorithms. There's a small difference between what you do in machine learning and what we do. The difference is between the type of the data. We usually use images, whereas in our cases, we don't have the images, we have the time series. So we apply machine learning on time series data mostly. I have all my degrees, PhD, master's, and bachelor's in mechatronics. Mechatronics, as you might know, is related to automation, and robotics is one good part of automation. So I'm specialized in brain-controlled robotics. I'm also a senior member of IEEE since 2017 and the vice president of IEEE Robotics and Automation Society of Pakistan. I resumed this position in 2018. I'm the associate editor of 5 ISI indexed journals, including IJCAS, which is International Journal of Control, Automation, and Systems. Some highly prestigious journals. In 2018, I won a Bill and Melinda Gates Research Award, and I went to Tokyo with my PhD student Hamad to receive that award. Actually, that was basically based on some research in Guinea-Bissau, which is an African country, where we used to, image the brains of children who do not get good diet or nutrition. So the effect on brain because of malnutrition is what I studied. So Bill and Melinda Gates Foundation is a charitable organization. It's an NGO. They funded our research. My name has been included in the Productive Scientists of Pakistan for 3 times. and that's the maximum time that you can apply. So I can't apply for it anymore. I have a total of 98 publications, so I'm waiting for my century. So I hope I get 100 very soon, and I have more than 2,500 citations. Right now, I'm sitting in Islamabad. Islamabad is the capital of Pakistan, and it's some 6,000 or a little more kilometers away from Malan. It's a beautiful city. It's surrounded by Margala Hills. Lots of greenery in here. I go to Margala Hills for hiking every weekend or even in the weekdays. So if you come to visit Islamabad someday, please do come to Islamabad and visit Margala Hills. It's a beautiful city. I have the honor to be at your university back in November 2018. I visited your university. There was a conference, SIET, and I was a keynote speaker in that university. That conference. So I visited your university and your city, and I purely enjoyed my stay there. It was a 5-day stay, but it's such a beautiful city, Malang it is. I also happened to visit Mount Bromo because I'm very fond of hiking and trekking. It was an amazing experience to see the crater of a live volcano. Really amazing. I wish to come back to Malang soon again when the situation gets better and it's safe for people to travel and meet along. My university, Air University, is one of the top universities in Pakistan. It's a flagship university of Pakistan, one of the national universities. And it's primarily administered by Pakistan Air Force. So it's very near to Pakistan Air Force headquarters in Islamabad. Just on the foot of Margala Hills, you can see the Margala Hills in this photo behind. And it's a very modern and new architecture. And we're building another campus as well in the heart of the city. Next year in December, we'll start shifting to that campus. And this campus will go to the Fazaya Medical College. So we'll have medical facilities in here. We have 48 programs in total. So by volume and by students, it's a big university. Coming to the contents of this presentation, as Professor Noman shared with me, I'll be discussing the anatomy of deep neural networks. We'll talk about the basics, the history, and then we'll talk about the feature learning. And then we'll go to the supervised learning, unsupervised learning, self-supervised learning, and reinforcement learning techniques. Well, when we talk about the history, it's impossible to forget this paper. Warren, Mikuloc, and Pitts. They were the two scientists, or in fact, Mikuloc was a neuroscientist and Pitts was a logician. In 1943, they wrote this paper. They basically tried to understand how the brain could process the highly complex patterns by using basic cells, which are, of course, the neurons, which are connected together to make complex decisions. So the single neurons are connected together and they can perform complex tasks. So they give a very simple model of a neuron. They call it MCP, Mikuloc and Pitts model. This model was basically based on mathematics and threshold logic. Pitts was basically a logician. So it was based on threshold logic. Now, this model was the first model that paved the way for future researchers for neural network research. It split it into two, actually. There were two approaches. One was to focus on biological processes in the brain, while the other one was to focus on the application of neural networks to artificially intelligent systems. As you know, artificial intelligence is a bigger umbrella. Learning is one part of artificial intelligence. And when we talk about learning, machine learning is the artificial way of learning. And the neural networks are one good part of machine learning. And the deep neural networks are one good part of the artificial intelligence or ANN. So, I mean, it's artificial intelligence covers a lots of things. Well, the main issue with this model was actually that it was a very simple model and there was a huge difficulty. It could only allow for binary inputs and outputs. So there was a provision for only binary inputs. Either the input could be a 0 or a 1. And also it used the threshold step activation function. We'll talk about the activation functions, and herein it just used threshold step activation function, which is very basic and is applied to binary inputs very easily. Also, it did not incorporate weights, or we could not weight the inputs, which is nowadays one of the specialities of deep neural networks. And also it lacked the mechanism for learning. There was no proper mechanism for learning this model. However simple, it is still considered as one of the first, solid effort in the field of deep neural networks and in the research in this direction. Later, in 1957, there was another paper published by Rosenblatt. Now, what Rosenblatt did was he used MCP, the previous model that we just discussed, and he went on to develop and introduce the first perceptron. You know, the perceptron is a single layered network, and he developed it in 1957. The perceptron could learn through the weighting of inputs. That was instrumental in the later formation of neural networks, because you can see later the neural networks were based on perceptrons, multiple layers and multiple input, output, etc. So a simple perceptron looked something like this, in which you can have multiple inputs and output, and those multiple inputs can have weights. So for example, A1, A2, A3, A4, and A5 are the inputs to this single layer system. And you can weight the A1, A2, A3, A4, A5 as well. And interestingly, you don't necessarily have to weight them equal. You can give different weights to different inputs. You see, when in our brains, I study brain because I do brain-computer interfacing. So I study brain a lot. I have to acquire signals from the human brain. So when we study brain, we see that we have different kind of inputs coming to neurons and different kind of outputs going out from those neurons. In general, if we have to do something, different inputs come and we assign different weights to those inputs. For example, if I'm feeling hungry, then there will be some inputs that will come to my mind. And some of those could be, you should go to the cafe. And there would be a certain weight assigned to it. Second would be, is your class time right now? There will be a certain weight applied to it. Number 3, do you have enough money to buy something for you? You will have some weight assigned to it. Those weights will be the deciding factor on which decision do I take, whether to stay hungry or to go to the cafe and eat something. So those weights depends on many people. If I and you have been given the same problem, we will assign different weights to it. And why would a human, 2 different humans, assign different weights to it? That depends on your upbringing. That depends on your history. So based on those inputs, we will make a decision and then act accordingly. So similarly, in perceptrons, what you have is different inputs and they have different weights. And based on those weights, a decision is made and given to the output. And these inputs may not be given equal weights. They can have different weights. And the perceptron may have learned to weigh the A1, A2, A3, and so on. Well, so this is the 1940s, McCulloch and Pitts model. Then that was the Rosenblatt model. And in 1970s, in fact, 1960 something, I don't really remember the year, Minsky and Papert, they wrote a paper which was quite skeptical of the limitations of perceptron. They said that a single layer perceptron cannot solve a nonlinear problem. And then came the XOR problem. So XOR problems, I mean, it seems very simple, but a single layer perceptron could not solve it. They said that you need to have multiple layer perception, and for multiple layers perception, the algorithms of the single layer, the activation functions of the single layer were not valid. You have to change them. So how do we change them? Those were presented as backpropagation algorithms in 1986 by Rommel Hart. So multi-layer perception and the method of backpropagation was then presented. Wapnick in 1993 actually wrote a paper first in Russian language and then translated in English language in 1995. He presented the limitations of learning prior knowledge, the curse of dimensionality, and the kernel functions. He was basically the inventor of support vector machines. Commonly used in classification problems, and of course, extreme learning machines, which are based on the concept of support vector machines. Then the pertaining neural networks are basically based on the works from Hinton and Rosalind in the 2010s. Well, this was some of the history of and the timeline of our field. Well, if you talk about anatomy, we can have an input data or image, and that input data image basically in the first layer, we can have a first feature maps after convolution. And those feature maps after pooling can be converted into a second layer, which is actually the first pooling layer. Based on those, another convolution can be performed to make a second convolution layer. And then we can have a second pooling layer. After that, we can apply whatever regression or classification model that we want to. For example, softmax logistic regression or the softmax classification problem to basically classify or decode. Well, talking about anatomy, we'll just discuss biological neuron model, activation functions, the architecture of neural networks, some pre-processing tips, initialization of weights, normalization, dropout, and loss function. Well, as I told you before, the biological neuronal model is basically, it looks something like this. The basic cell in a brain is called a neuron. And that neuron basically consists of few parts. This body is called soma. Inside soma, we have a nucleus. Then we have an axon, and along the axon, the messages are transmitted. Then we have axon terminals, which are connected to the dendrites, the inputs of the other neuron. So these are the inputs or the dendrites of the neuron. This part is nucleus, the decision-making part. This is axon through which the messages flow, and these axon terminals are connected to the dendrites of the next neuron. And there's a chain of many such neurons interconnected. When ensembles or group of neurons fire, some electrical potential is generated, and we try to get that electrical potential. That in a so-called method of electroencephalography, which is very commonly used in brain-computer interfacing. Now, replicating this model to an artificial model, we get this thing. Herein, we can see that we have different inputs like x0, x1, and x2. These are different inputs of the of this main cell body, and these inputs can have different weights. For example, W0, W1, and W2. And as I told you before, these W's can have different values and different weights. Then the decision has to be made based on inputs and some activation function, some decision-making function. Now, that activation function can be decided, there can be many activation functions, and based on those, decision is made and conveyed to the outputs. So this is the biological neuron, and this is the mathematical model, a simplified form of mathematical model of a neuron. In a human brain, there are millions of neurons, all interconnected. We, as students of neuroscience, have not been able to fully describe the function of all neurons in the brain. So some people say that we should go beyond the skies and go to the planets abroad and Mars and Jupiter and see what's happening there. But unfortunately, until now, we have not been able to image and see properly what's inside a human being. So we can functionally, we can structurally see what's happening. We can see the structure of the brain, but the functionality of the brain, we're not able to fully understand till now. That's the reason why most of the diseases related to the function of the brain, they do not have any permanent solution. For example, epilepsy. You can control or restrict the body movements because of epilepsy, but you cannot actually control epilepsy. Same goes for the Parkinson's disease, the Alzheimer's disease, and many others. Although we are trying and we have been able to do some research to enhance the working memory of the people. So what we do is we externally stimulate through direct current or magnetic field, and we try to improve the working memory. We try to improve what we call N-back test. Can you remember 3 words back what was said or not? So we test in that way, and it has been shown that using transcranial magnetic stimulation and direct current stimulation, giving a direct current to the brain in particular way and in a particular limits can actually improve your working memory. But we have not been able to see the permanent memory yet. So in our brain, there are 2 types of things. One is the RAM, just like a PC, and one is the ROM. So we can see what's happening with the RAM, but we are not able to understand fully what's happening with the ROM. So there has been lots of research, and we are trying to dig into it and see what will happen. But so far, there has not been much, we can't say for sure that we have been able to study the function of the brain in full. Anyway, so that's how a neuron looks like, and millions of these neurons are connected, and based on these neurons, we have actually developed the artificial neural networks in a way that our brain thinks. In a similar way, an artificial neural network should be able to think. You see, when people, lots of people here ask me that artificial intelligence is going to take over, what do you say about it? So I say, what do you mean by they will take over? Would it be for good or would it be for bad? If it's for good, excellent. We want it to be done. If it's for bad, then we should train it in a good way. You see, we do what we learn. If we teach computers and machines bad things, they will do bad things. If we teach them good things, they will do good things. We learn from the environments. The machines, the AI systems will learn from the environment. If they see bad things happening in the environment, they will learn bad things. If they see good things happening in the environment, they will learn good things. So we need to be good first, and then machines will be good, trust me. If we are bad, machines will be bad. Okay, so talking about the activation functions, there can be many. There can be many types of activation functions. For example, a sigmoid. What does it do? A sigmoid function basically restricts or squishes the real numbers into a range between 0 and 1. Similarly, the tan-h, it squishes the real numbers between -1 and 1. So what happens is, in the activation function, they are taking each and every number and passing it through a function. So the data is coming, it is being passed through a function, and an output is generated. Based on that, we make the decisions. Though there can be several mathematical operations. Some of these that you may encounter is very common one, sigmoid function and tan-h function. There's another one which is quite famous. You must have heard about it, the ReLU, R-E-L-U. Now, the ReLU actually stands for Rectified Linear Unit Activation Function. If you see the name rectified, well, rectified means that it blocks all the negative data. So for x less than 0, it will give no output. It will be at 0. So you must have heard about the rectifier that we use in electric circuits, that is used to convert the AC to DC. So what happens is that it lets the positives pass and it blocks the negative data. So similarly, when we say the rectified, so it means for x less than 0, all the values of the output would be 0. For x greater than 0, it would be linear, and not only linear, but also with a unit slope. So I'll go again. For x less than 0, it would be 0. And for x greater than 0, so we have an x-axis in here and output x-axis in here. For x greater than 0, it would be linear with a slope of 1, with a unit slope. So rectified, linear, unit, ReLU. It's rectified and has a linear with a unit slope. You can see it here, which is 0 when x is less than 0, and then linear with slope 1 when x is greater than 0. Well, several times it has been shown that different activation functions can have different effect on the results. And it has been shown in this particular paper that if we use ReLU, it will have 6 times more improvement in convergence as compared to when you use tan-h units. So you'll find many studies which actually compare the performance, the output performance when the activation functions are changed. Well, of course, when you make neural networks, you have several layers to it. In a simplest form, in neural networks, we can have 2 layers. And then in here, you can say the 2-layered neural networks. One is the hidden layer, and there's an input layer, and then we have an output layer. And in here, we have 3 layered. We have 2 input layers, an input and output layer. So this one is a 3-layered network with 2 hidden layers. So what would be the effect of these tools? You see, there can be an effect of activation function on the outputs. Similarly, there is a lots of effect of hidden layers on the output. So it has been shown that using more hidden layers in certain problems, you can classify with more accuracy. The demerit is, of course, is that you get to I mean, you get a lot of data, you have more computation, and there's a computational cost, which is a lot. So it would be best if we could do it with minimum possible layers in the best computation time. But in some problems, it's not possible. For example, this one. Herein, you can see that there are two classes that we want to classify. It's a two-class data. One is in red color, these dots, all the samples, these are in 2D. And then we have in green color. So these could be any features on x-axis and y-axis. There's a 2D representation of the feature space of these data points. When we use 3 hidden neurons, these were the results. So this area was given to the class red, and that area was given to class green. However, you can see there are certain outliers. This does not belong to class green. This, and this also does not belong to class green. So we have less accuracy. But when we added some more hidden neurons, some more layers, so what happens is when you add more hidden neurons, so what happens is that this area increases in a way that it covers more of the red points. And similarly, when we go up to the 20 hidden neurons, essentially you can see, in this one, you can still see some outliers. This has been covered, but you still have some outliers. And when you go to 20 hidden neurons, you can see that essentially all the area covered by the training data has been covered. Now it's up to the testing data. If the testing data comes here, it will be classified red or pink, whatever color it is. If the testing data comes here, the features of that data comes here, it will be classified as the green one. Of course, we can still have some outliers and some errors. It's not 100% accurate, but much better using 20 than 3. Of course, we do it at the cost of the computation and, of course, time. Before actually going for classification or the learning problem, we need the data to be in a certain form. We need to pre-process the data. The data that we get, the time series, is mostly from the sensors. And even the images are from a special kind of a sensor, which is a camera. That data can contain several noises. The noise is an unwanted signal in the data that we don't want. You know, if we are seeing or focusing on something with our eyes, we can see several other things in the surrounding. If we don't want to see them, those will be considered as noises. Similarly, in a cocktail party effect, you're interested in listening to your friend, but there are ambient noises like music and other people talking. Those are actually the noises, and you're not interested in those. When you become interested in the music, then that becomes your signal, and your friend talking becomes your noise. It's all relative. What you focus on is the data that you need, and everything else is a noise. So we need to pre-process it to remove noises and to do certain other, to make the data suitable for further processing. If you see this data, this is an example of an original data. And this data, so there's a difference between the two. So what happens is that this data has been centered on both dimensions. So this is a 2D data. You have the data spread on x-axis, and you have a data spread on the y-axis. So this data has been, you see, the mean of this data on both dimensions has been moved to 0. So if you move the mean of this data on x-axis as well as y-axis to 0, then we call it a zero-centered data. Please remember that in case of a zero-centered data, all the dimensions, the mean in all the dimensions should be at 0. So in that case, we call it a zero-centered data. It is not necessary that the data spread on x-axis and y-axis is the same. You see, the data spread in here is different and the data spread in here is different. However, when we normalize the data, what we do is we try to not only center the data, but also fix it between certain limits on both axes. And hereby we can say that the scatter on both axes or in general in all should be equal or similar. So in this one, you can see that perhaps it has been normalized between -1 and 1, I guess, I don't know. So, or something else. So it has been normalized within certain range. It can also be scaled by its standard deviation, which is the case in this photo. In this case, you can see that these red are of unequal length, which means in both dimensions, the spread is different. But in this case, you can see that the red lines are of same length, which means that in both dimensions, the spread of the data is same. Also, we can perform decorrelation of data and whitening of data. Well, decorrelation of data is actually, if you have this kind of data, what you do is you perform principal component analysis. Principal component analysis is basically a dimensionality reduction scheme. The data is centered at 0 and then rotated into the eigenbases of the covariance matrix, which consists of the data. This decorrelates the data. There's no correlation between the two. In this one, you can see that the data is correlated. There's a trend or correlation between the data X and Y. But in this one, it has been decorrelated. In the right one, you can see that each dimension is additionally scaled by the eigenvalue. When you do that, it is transformed into a white data, similar to what you see in a white noise, that it is Gaussian in nature. So this data can be transformed into a white data when you scale it. In principal component analysis, what you try to do is you try to actually get the principal components or the eigenvectors, and the top eigenvectors are the vectors in which direction, if the data is projected, they will have the maximum variance and will conserve the maximum information, as you can see in here. So if you see this image and you select any top eigenvectors, you'll get something like this. However, if you use PCA and select the eigenvectors which correspond to the highest eigenvalues, and you can get essentially the same thing with a very minimum amount of data. So in dimensionality reduction, what you try to do is you try to reduce the amount of data by essentially trying to conserve the information that the data has. So even if you classify the original data or the reduced data, there's not much difference between the classification accuracies, or there's not much difference between the resolution, but the data is reduced, so there's a lot of difference in the computational cost. So that is the main aim of principal component analysis. Principal component analysis is not only used for dimensionality reduction, but by reducing the dimensionality, it can actually act as a classifier as well. Particularly in the time series data, what we do, we have in our previous researches used principal component analysis, and we have been able to use PCA as a classifier to classify the different kind of data. Then let's talk something about feature learning. You know what features are. Features are actually the attributes based on which you can discriminate between certain things. For example, if you want to discriminate between a car and a motorbike or a scooter, you would say that a steering wheel is a good feature. True, because a steering wheel is in a car, but not in a scooter. On the other hand, if you say that you'll add a wheel or a tire as a feature, that might not contain a discriminatory information, because even the car has wheels and even the scooter has wheels. On the other hand, if you say number of wheels, if you set number of wheels as features, that's a good feature, because most of the scooters have 2 wheels and most of the cars are of 4 wheels. So similarly, what you have to do is you have to actually get the discriminatory information based on which you should be able to distinguish the data. Conventionally, what we did was we used to actually engineer the feature. We used to extract the feature, and we used to extract the features based on observation and manual selection. What we used to do was, for example, in the example of time series, we can see the graphs and we can see the statistical values on those graphs. What kind of, for example, there's a graph whose mean is at a higher level, and there's another one whose mean is at a lower level. So we can see that mean could be one good feature. Similarly, we can see that the variance of data in our time series data is more than the other one. So we can use variance, skewness. The data is skewed to one direction. It has some cortices. All the mean the first moment, the variance second moment, skewness the third moment, and cortices the fourth moment. We can use all these peak values, peak to peak values, root mean squared values, and all such values as the features. Similarly, for image processing, you can manually select the feature. For example, you want to do facial recognition. So the distance between the nose and the lips, the distance between the 2 eyeballs, and this and that, you can use those features actually. Those are actually manual selection of the features. Based on those features, you feed those features, not the original data, you feed those features to the classifier, and the classifiers are able to distinguish between the different features and give you the results. This is usually the case with the shallow networks and the conventional machine learning. However, when we talk about deep neural networks, they are actually able to learn features and classify. We call it end-to-end learning and classification as well. We just need to provide the raw data. It will learn or distinguish the features on its own, and based on it will make a decision of a classification and give you the input, the output. You don't really need to extract the features manually. The algorithm will learn the features on its own, and based on that, make the decision. It's important to know what is training and testing. In any kind of machine learning problem, you have some data based on which you tell the algorithm what should be done, or you train the algorithm. You see, if you don't have any data to train, you will not get anything at the output. This is exactly what I was talking about when I talked about your training matters a lot. So, in here, it is famous that the sons and the kids of army people go to army a lot. You see, people say that, oh, maybe they have connections and links in army. That's why they get their sons and kids recruited into the army as well. But I don't think so. This is because of their training. From their birth, they have been seeing the system in their house, and they're trained in such a way that there are lots of chances of the army peeps to go to army. Same goes for engineers and doctors. We see that the kids of the doctors want to become doctors, most of them. It's because they've seen and are trained in such a way. Similarly, when we talk about ANNs or AI, we need to give a training. If we have given a good training, we expect a good output. If we've given a bad training, we expect a bad output. So we get lots of data. For example, in this particular example, we have to discriminate between a dog, a cat, and a honey badger. So we give it lots of images of dogs, cats, and honey badgers. We train the network, and once we train it, the model is prepared. Then when we have a new instance, for example, this data, this will pass through the same model, and based on it, it will tell whether it was a dog, a cat, or a honey badger. If it was a dog and it was correctly classified, then we'll say it's a hit. Otherwise, it would be a miss or an error. So yeah, it's extremely important to give a good amount of training data, and a good discriminatory features are acquired by the network through data. If these two conditions are met, the output of a new instance would be great. So yeah, so there are two approaches in one which we engineer the features ourselves and select those features. It's a tiresome process. We have to do it on our own based on observation or previous data or things like that. And then we have to train the classifier based on features directly, not the input raw data. And it gives the output. And the other one, we have end-to-end learning, in which the features are learned on its own, and the classification is also performed. You can see from here as well, there's an input, there's a feature extraction thing going on, and then we can have a classification. So ANNs in general can be used in both settings. I mean, they can be used, features can be given to those as well as they can be used for end-to-end learning. Deep learnings are mostly, I won't say always, mostly focused on end-to-end learning, and in which feature extraction is performed and classification is performed on its own. You see, generally speaking, we divide machine learning approaches into three: supervised learning, unsupervised learning, and reinforcement learning. However, nowadays, we say that we have semi-supervised learning as well, and we have self-supervised learning as well, which is kind of, a subset of supervised and unsupervised learning, but not purely the supervised and unsupervised learning, a little different. What is supervised learning? You see, in supervised learning, the labels of the desired output are given. So a neural network is set to learn supervised if the desired output is already known. Or in other words, we say that we have a labeled data. You know, my daughter, her name is Zaveria. She was very little, only few months old when we went to South Korea. There were certain fruits and vegetables that are here in Pakistan, but not in South Korea. So when she came back, so I tried to test her. So because my mind was all made up of neural networks, so I thought, why not test her? So I showed her certain vegetables and fruits which she had never seen. Tell me, what is the name of this particular vegetable or fruit? She was not able to tell me because she was never trained on it. but she made a guess based on what labels she already had in her mind. For example, she did not have seen a pear, so she said, it's probably an apple. Then I said, no. She said, it could be guava. But she could not say pear because there was no label present in her mind. So you see, similarly, if you have a shop, a fruit shop, and there are lots of fruits in there, and you tell someone to separate out only apples or only bananas, knowing. So someone's mic is on, and it's kind of disturbing. So it would be best if you could kindly mute the mic. Okay, okay, that's that. Thank you very much. Okay, so I was saying that there's a scenario in which you go to a shop, and the shop is full of many fruits, and you're asked to separate out only apples or bananas. And you know what are apples and bananas. You know already how an apple looks like and how a banana looks like. You have the labels. This is a part of supervised learning. You know already how they look like. You extract them out. So what we do is we train the data and tell beforehand during the training this data belongs to this particular class. This is the label of that data. That is called, and it learns from it. And then when the new instance comes, it tries to predict based on the training data. And this particular instance is basically called, supervised learning. In supervised learning, collection of data and labels is important. Supervised learning is not very practical in a sense that if you have to get the images, you have to get lots of images. If you have to get for example, I've done some work on detecting the ECG signals automatically. Now, for supervised learning, I need to get ECG data from all the hospitals, then tell that this ECG data corresponding to this particular disease, and then lots of labels. So this is a tiresome process actually. Labels are not always available. So most of the practical aspects are actually unsupervised. How do we do that? I'll tell you that as well. So in case of supervised learning, we have an input. This is actually a block diagram of adaptive supervised learning, and I'll tell you how does it work. Now, this is basically our network in which we have an input, we have layers, and we have output. That output is compared with the desired output. If there's an error function is generated based on which an optimization is performed and given back to the networks by changing the weights. If not, then it carries on to the next instance or the next data point. That's how a supervised learning method works. Then we have, supervised learning can be efficiently used in transfer learning. Transfer learning, so to say, is actually what we do is we have the labels, we have the data, a large amount of data on which we perform the model training, and that is used on another data, which is a local and a small data. So on our local and a small data, we cannot train a model efficiently, but because of the similar nature of the data, if the data is of similar nature, what you can do is you can get from the public data sets available, you can train the model, and by using the transfer learning, you can use the same trained model on your local data, and the classification accuracies would be on par. Of course, we have to perform some fine tuning based on our data as well, and that I'll tell you in the next slides how. This is actually very efficient way because you do not always have a lots of data. For example, if I want to do some facial recognition of particular ethnicity of people, and I have some people here at Air University Islamabad, I can't do that because we have just 5 or 6 of those people. But on a publicly available data set, if we have lots of people available, you can train on that and then test on our local small data. It should work fine. So what we do is we get the source data and we do the source modeling. And then we have the source label. We transfer this model to our target or the new data, which is smaller in number. This is a huge data. This is not so huge. Apply the same model and try to get the labels or the targets. Well, if we have a small data set and we have a similar data set, then we do not need to have some, the load on our classification and features is not so much. But if we have a small data set and we have a different, inherently different data set, then the load on the, classifier and feature learning method would be higher. In case of a large data set, even with similar data set or a different data set, we just need to do fine tuning and nothing else. We don't need to engineer the features again or learn the features again. So larger the data set it is, better it is. I mean, you must have heard very commonly that you need to have a large data. The larger the data you have, the better you have the results. It was not the case in the conventional machine learning actually. Wapnick and others actually showed the curse of dimensionality. If the data dimension increases above certain level, it actually starts decreasing the classification accuracy and so-called curse of dimensionality. But that is not the case in the deep learning methods. The larger amount of data you have, the better results you probably would get. Just a moment, please. All right, so there you go. I mean, so there's another example of a strategy that we use in transfer learning. You have a source data you can get from ImageNet and everything. You can train a source model and you can get the labels based on big data. You can transfer the same model to our local data set, which is a small data set, and the target data will get the target labels very easily. So these are basically just available open source data sets, mostly labeled. What is fine tuning and how do we do that? I mean, for example, you have lots of data available for training, the publicly available data set. You have a random neural network, you train it, and you have a trained neural network. Now, when you apply on a local data set, what you have to do is just apply on your data, and it will be tuned as per your data as well, and you'll have a trained neural network ready. You do not need to train on all the images. You just need to train on the images that you have. So what you can do is, we call it a technique, which is a freeze layers. So in which what we do is, to accelerate neural network training, we can progressively freeze hidden layers. During transfer learning, the first layers of a neural network are frozen, while the end layers are left open to modification. So in this way, we accelerate the neural network training. And of course, the aim is to cut down on the computational time for training while losing not much on the accuracy. So in this way, if you see, the accuracy would essentially not reduce much, but the computational time for training will be much reduced. And of course, it's not fully training. We are doing a fine tuning in this case. So we can freeze certain layers and train on just a few end layers and see what the result is. So these are some of the techniques that can be, there's certain more techniques that can be used in fine tuning, but that's the most common one. Then we go to the unsupervised learning. I mean, whenever we talk about unsupervised learning, clustering comes straight to the mind. You know, I just gave you an example of a scenario where you enter a fruit shop and you have to separate out the banana and the apples. Now imagine there's someone who does not know how a banana or an apple looks like, and we move him into that shop and asks him to separate out a banana and an apple. Can he do that? Not on purpose, not specifically, but what he can do is, based on the patterns, he or she can separate out all the bananas, all the similar looking things. He might not know this is a banana, he might not know this is an apple, but based on the similarities with each other, he might be able to discriminate or cluster them out, group similar things in a different way. We play in such a way. So I have a little company here, which is called Robo Miners. We teach robotics to young people here, young kids from age 5 to 15. So we do such experiments on such people. We ask them to separate out things based on their shapes, and they can do that. That's basically, they don't know what shape it is. They don't know what is a triangle, what's a pentagon or a hexagon. But based on the similarities in the shape, they can separate out the data. And that's basically a good practical example of unsupervised data, in which you don't have the labels, you don't know the names, but based on similarities, you can somehow separate them out. Well, the most commonly used unsupervised learning algorithm in conventional machine learning is basically k-means clustering. And that clustering is basically done by randomly. What we do is we randomly select 2 data points and then find out the Euclidean or Mahalanobis or another kind of distance. In its simplest form, we find out the Euclidean distance of that data point with the other data points. The data points which are near to the center, or we call it the centroids, are separated out. Then we calculate the centroid again based on new observations, and the process is iterated until you get a convergence and there's no change in the data. So in this way, the clusters are separated. Centroids, the data near to one centroid will be classified as one cluster. The data near to another centroid will be classified as another cluster. And of course, when I say near, we're talking about the Euclidean distance, because we are not just in 1D, where we can be in 2D or 3D. So that's how unsupervised learning works. In deep learning, artificial neural networks and deep learning, what happens is that we used a very commonly used method, which is called autoencoding, or the autoencoder. What an autoencoder does is it encodes the data, and it somehow mostly reduces the dimensionality of the data and represents it in a latent vector space. By removing the noises and unwanted data, it actually reduces the dimensionality by separating out the clusters. So autoencoder is one of very, famous methods of performing unsupervised learning in the deep learning networks. Just a moment, please. Oh, my throat becomes so dry that I have to drink water in between. So you see, in a physical class, you can see how engaged the participants are. In an online class, I can't see how have I engaged the participants, are they really listening or sleeping? I can't tell, right? So there are certain merits and demerits of teaching online. Although online teaching has given us lots of opportunities for distance teaching and lots of scenarios where you can learn from distance, but there are some demerits as well. A teacher, a professor can engage a class physically, perhaps better than he or she can do in an online setting. In a physical setting, he can ask questions, you can give answers, and there can be, an interactive learning. The chances of such learning are quite low in the online setting. So in an online setting, only the professor has to speak and speak and speak, and his throat becomes so dry that he has to drink lots of water, or perhaps an energy drink, a Gatorade perhaps. Anyway, so that's how we do unsupervised learning. Then, as I told you before, there's a certain thing called semi-supervised learning. Now, semi-supervised learning does use supervised and unsupervised both learning. However, there's a difference. The difference is that in case of supervised learning, we have all the data as a labeled data available. In unsupervised, we have no labels available. In semi-supervised learning, we can have labeled data as well as unlabeled data. Generally, in fact, mostly, in semi-supervised learning, the labeled data is quite low in number and unlabeled data is high in number. We can do two things here. I mean, different people have done different things. What we can do is, number one, we use the labeled data to train and generalize on unlabeled data, or the labeled data to generalize and predict the new information. Or in the other hand, what we can do is we use unlabeled data to do clustering and then use the labeled data to label those clusters. So based on labeled and unlabeled data, we can make a model and get the results. So, and it can be used in different scenarios. One of the scenarios could be that you collect and process the unlabeled data first. You train, improve, and deploy the methods, and then you get the label using the data that you have available as the labeled data. In another scenario, what you can do, what we have done actually in the time series analysis, what we do is we just get the labeled data and generalize that labeled data to train the model on that labeled data to generalize on the unlabeled one as well. Of course, that is not a very efficient method if you don't have a huge number of data points and if you're not playing with the time series. In time series, I mean, these methods can be effectively used. In time series, certain methods can be effectively used, which cannot be very efficiently used in the image processing or other analysis. So, so this is one of the scenarios in which semi-supervised learning can work. Okay, and then we have self-supervised learning. I mean, that's another thing, and this concept is mostly associated with the deep learning. This is very little associated with the conventional machine learning. In self-supervised learning, I mean, self-supervised learning is a means of training computers to do tasks without providing labeled data. We don't provide the labeled data. The basic concept of self-supervision relies on encoding an object successfully. In self-supervision, it encodes an object successfully, and then based on the missing information and pretext, it predicts the object. So an algorithm which is capable of self-supervision must know different parts of an object so it can recognize it from any angle. You usually rotate it to different angles, and you make it learn. And then if you get a one part of it or two parts of it, it can predict the other parts of it automatically. Now, this is actually included in self-supervision, and it's very commonly used in NLP and speech and text recognition. So, for example, you say a quick brown fox jumps over, a lazy, whatever it is, a dog. So if you skip just one word out of it, but because of the pretext, it will know, it will have learned and know what has been skipped. So in case of object or face recognition, what you do is it has to encode it from all the different angles. And if there's some missing part, you usually divide it into grid. And then there's a missing part in a grid, and it can predict it because it has all learned it on its own. So this is a kind of self-supervised learning. Then reinforcement learning. In reinforcement learning, the idea is based on reward or punishment. If someone is going in the right direction, you encourage him or her. If he or she is going in the wrong direction, you tell him, no, that's not the way to do it. So by getting this feedback, it can change or alter the direction. That's exactly what we do with the model. So if it's going in the right direction, if the error rate is less, then we will reward it. If it's predicting right, we'll reward it. If it's not predicting right, we'll punish it. We did it practically on some mice. What we were doing was we were trying to control a rat or a mouse. It was a rat actually, through computing. So what we were doing was we were externally, electrically stimulating the motion neurons of a mouse, of a rat, that makes him turn left or that makes him turn right. So of course that rat has a free choice. It can decide to obey or disobey us. But if it disobeys us, we ask it to move right and it moves left or does not move right. What we do is we hit the pain center of the neuron and the mouse feels pain. So, and if it does what we want it to do, we hit externally, electrically, we hit the pleasure center of the neuron and it feels good. So by positive and negative reinforcement, that rat learns that it has to obey us, and its nervous system makes it believe that it will get pleasure if it does what he's been asked to do. So eventually the mouse just leaves his free choice or free will. That's exactly what we do with the models. We have inputs, we have a deep neural networks, we have outputs. That output goes to the environment. We have a reward or a punishment. Based on that reward or a punishment, we can adjust the weights. And there can be different formulas or different schemes, methodologies in which this reward and punishment thing can be done. One of them is given here. For example, this is the new value. This is the current value. And using this formula, you can do, this is the learning rate. This is the reward. This is the discount factor. This is one way of doing it. There can be many ways of doing rewarding or punishing. And then you can take this example as that of a person who's moving without seeing anything, but by observing using other 4 senses, or maybe more. We believe we have five senses. We might have more than five senses. So using other senses, it is actually knowing from the environment what he's going through, whether he's going in the right direction or not. So you might have played this game as a young kid in which your eyes are blanked by a handkerchief or some clothes, and you have to find your peers. So what you do is you try to find them out using the voices, the feeling of the environment. So in reinforcement learning, you have the main agent, which performs the action, and the environment, which by observation you get whether it's going in the right direction or not. If it's going in the right direction, a reward is given. If it's not, a punishment function is generated. That's how reinforcement learning in general works. Oh, that's all from my side for today, and I'm happily available for any questions that you might have. If you have any questions, please feel free to ask. I'd be more than happy to respond to you, to your queries. So do we have questions? Well, if not, I would hand it over to my co-hosts.
Okay, thank you, Mr. Noman.
You're welcome, Professor. You're welcome. So, are these students very shy of asking questions, or they're much clear of what we studied?
Yes, I think they are still shy, and then maybe they are very shy to ask you in English.
Okay.
Okay,
What
right.
you can do is you can share my email or whatever means they feel comfortable with, and if they can't ask directly in English, perhaps they can write me the question later anytime they feel convenient, and I'll be happy to respond them via email or whatever means they prefer.
Oke, teman-teman semuanya, kalau misalkan ada pertanyaan, silakan di email Dr. Norman, ataukah nanti bisa kalau ada yang mau chat, silahkan. Jadi kita tadi sudah mendengarkan materi tentang berbagai macam cara pelatihan di dalam deep learning. Itu tadi ada supervised, unsupervised, self-supervised, dan juga reinforcement learning. Yes, Dr. Noman have presented well. So he gives you the big picture about how deep learning works from supervised, unsupervised, and self-supervised, and then reinforcement learning. Okay, do you have any question? Okay, if you have any question, please email Dr. Noman, and then or you can send the question to me, and I will deliver to the Dr. Noman. And then maybe it's the time Dr. Noman to finish?
Yes, I'm done. I'm done.
Okay, okay. Because it's going to be a Maghrib time here,
Okay.
so soon. So maybe they are preparing for prayer and another something.
Okay. Okay.
Yeah. Okay.
Do
Thank you.
too.
Yes. And then don't forget for the next meeting, also with Dr. Noman with another materials. So for there are another member of class attended here. So this class is open for everyone, maybe without grades for you. For the students, you will be given grades for attending this class. Okay, so if you have no any other question, we give the thank you for the Dr. Man. Maybe Mr. Aditya, you can deliver some speech before closing.
Okay, so thank you very much for Dr. Noman Naseer for your kind material or your kind lecture. I believe it will open many things to our students, and hopefully we can meet with Dr. Noman at the next week, maybe, Dr. Novanto?
Yeah.
Yes, yes, still with
Yes,
Dr. Noman.
obviously. We will meet with Dr. Noman in the next week. And after that, the student will meet with Dr. Novanto Yudhistira again. So once again, thank you very much for your kind contribution to our student. So hopefully we can meet in the next week. So thank you very much.
Okay. Most welcome. It's always a pleasure. Thank you.
Okay. So shall we close the class, Dr. Novanto?
Yes, please.
Oke, so terima kasih banyak atas atensinya teman-teman yang sudah hadir di kelas ini dan juga Bapak Ibu dosen yang mungkin juga berpartisipasi sebagai peserta di sini. Kita akan bertemu lagi dengan sesi kelas ini minggu depan dengan link yang sama. So terima kasih banyak. Kalau ada pertanyaan nanti bisa disampaikan lewat Pak Yudis, kemudian nanti bisa diteruskan ke Dr. Noman. Terima kasih banyak. Saya akhiri sesi hari ini. Assalamualaikum warahmatullahi wabarakatuh. So see you guys and have a good time.